Hi, now, we would like to discuss current tendencies and developments of wind turbine blade materials. We will discuss the following topics. Failure of wind turbine blades, its mechanisms, and requirements toward blade materials. Recent developments in resin matrix and fibers. Blade coatings and erosion protection. Computational modeling in the development and optimization of wind turbine blade materials. Recyclability and sustainable solutions for wind turbine blades. But what is the problem? Climate change is one of the biggest challenges of our time. A large part of the greenhouse gas emissions is attributed to the supply and use of energy from fossil fuels. A transition from fossil fuels to renewable energy is the way to reduce the energy-related carbon dioxide emission. Expansion of renewable energy is one of the key elements of the strategy of mitigation global warming. For the next years and decades, large expansion of wind energy is planned. Global wind power market is expected to reach 69.7 thousand megawatts by 2027. European Commission raised the EU's renewable energy target from 32% to 40% by 2030, seeking to build 451 gigawatts of wind power capacity by 2030. USA plan massive expansion of wind farms off the coasts, planning to generate 30 gigawatts of offshore wind in the US by 2030. To some degree, a wind turbine became symbolic for new, environment-friendly, renewable energy generation. One can see it as background on TV news when one reports about new development in green industry or climate protection. In a YouTube clip showing continuation of Game of Thrones story in modern times, wind turbines are seen behind the damaged Titan of Bravos at Westeros. Such large expansion of wind energy sets several important challenges from materials science viewpoint. First, the durability and lifetime of wind turbines should be extended. Wind turbines are large and expensive structures, and it is just too expensive to replace them every 25 years. Low weight of blade composites is in fact related to the lifetime extension. Lower weight means lower load on blades, and thus longer lifetime. Another important requirement is easy and reliable maintenance technology. Further, now the sustainability and recyclability of wind turbine blade materials became especially important. But even now, the operation and maintenance costs of wind turbines are very high. They take up to 25% of levelized costs of energy, making wind energy more expensive and less competitive. Repair of wind turbine blades can be required every 2 to 3 years, and each of them cost thousands of euro. Thus, materials for wind turbines must be improved. Additional research studies are necessary. But why are the maintenance and repair costs so high? What are the mechanisms of wind turbine failure? Let us consider it for wind turbine blades. Let us look again at the wind turbines. There are several common tendencies in the wind energy development. Larger and larger wind turbines. Offshore wind turbines. Deep water locations. A few decades ago, most of offshore wind turbines of the world were located in limited area between Scotland, Hamburg, Denmark, and Norway. Now, wind parks are built in monsoon area, in Far East, in hot area near India and Arabic Peninsula, in North Sea. These locations are not very maintenance friendly. The winds are stronger. Monsoon and typhoons represent additional loads. Larger rotor means bigger swept area, and more energy generated, but also, higher blade tip velocity, and more surface degradation. How, and why, the wind turbine blades fail? Wind turbine blades are subject to complex environmental and mechanical loading during their service time. But they can also fail due to extraordinary events, like transportation damage, lightning strikes, bird impact. Several regions of blades are especially susceptible to degradation during service time. Leading edges of blades are subject to rain and hail erosion. Transitional regions, for instance, ply drop, area of transition from cylinder to aerofoil, tend to show delamination of composites. Adhesive joints can debond, and it can trigger buckling of structure. This failure mechanism can be observed in trailing edge or at web to spar joint. DTU Wind, and our colleagues from Indian Institute of Wind Energy, carried out survey among service teams, on frequency of observation of different failure mechanisms. Leading edge erosion, is most often observed mechanism, over first service years. Wind turbine blades, are structures, built from various elements, among them, single skins, sandwich structures, and adhesive joints. The often observed damage mechanisms of blades include leading edge erosion, adhesive joint degradation, trailing edge failure, buckling, delamination, and blade collapse phenomena. All the damage mechanisms can be triggered by manufacturing defects available in the structures. Mechanisms of structural failure of wind turbine blades include structural collapse and buckling, delamination in tapered areas, and ply drops, adhesive bond degradation, and buckling in trailing edge and skin spar. The most commonly observed manufacturing defects include wrinkles, fiber misalignments, fiber waviness, delaminations, debonding on interfaces, voids in matrix, voids in adhesives. But how often are different defects observed? Here, we can again refer to our survey, carried out together with Indian Institute of Wind Energy. It can be seen that defects in coatings are observed quite often. That can explain why the erosion of blades is most common damage mechanism. Further, interface defects, like delaminations and debonding, build the largest group of blade defects. This is an interesting conclusion, potentially useful. When we remember that composite buckling is triggered by weak interfaces, it can give us a hint how to improve the blade quality. Manufacturing defects play critical role for failure of wind turbine blades. Voids and microdefects available in coatings trigger the erosion of blades. Wrinkles, misalignment of fibers, as well as voids in resin and dry places reduce the compressive strength and can trigger buckling of composites. Voids, and debonded regions, in adhesive joints, can trigger fatigue damage, and then debonding in spar, skin joints, or in trailing edge. So, what are the most important developments in composite technology? Here, you see the short overview of available fibers groups for structural composites. The main direction is the transition from somewhat heavier glass fibers to lighter and stronger fibers. There are extra strong glass fibers, which are however, more expensive, non-bio-based, and non-biodegradable. Bio-based, carbon fibers, are still much weaker than pan-based carbon fibers. For now, carbon fibers seem to be the default solution for lightweight structures. For instance, reducing weight of wind turbine blades reduces gravitational forces on the blades, thus increasing the blade lifetime. Even fully bio-based composites will require additional carbon reinforcement to ensure strength, similar to glass fiber epoxy. An interesting solution is hybrid composites. For instance, LM Wind Power manufactured a wind turbine blades a few years ago using hybrid carbon plus glass composites. The blade was a world largest at this time. Hybrid composites allow combining the advantages of both fibers. However, it should be said that they are more difficult to recycle. Bio-based structural composites. The composites, made from natural fibers, and bio-based resins, can potentially replace the common glass fiber composites. Sustainable composites should include bio-based, recyclable resins. Several companies and groups developed bio-based and/or biodegradable resins, among them Rilson, Altuglas, and others from Arkema, FDCA, and PEF from Avantium, adhesive resins from Cambond, and so on. Typically, they are based on polylactic acid, thermoplastic starch, polyhydroxyalkanoate, and cellulose. However, PLA degradation in water can limit the use of PLA-based systems for durable and long-life structures. Epoxidized linseed oil was shown to be a promising substitution of the petroleum-based resin, thanks to similar hardness and improved toughness. Nanoparticles can build conductive networks, layers or fibers, creating the conductivity path in the material. The electrical resistance of the materials with nanoparticles is changed under deformation and failure, due to changing, eventually broken, contact between adjacent carbon nanoparticles. The tunneling resistance between two adjacent nanoparticles also changed, due to changed distance between them. This led to the idea to design sensing network in composites. Similar to the nervous system of humans. There have been dozens of European, American and other projects seeking to develop such embedded sensing system for aerospace and other applications. Self-healing composites represent another, interesting option for the wind turbine blades. You might remember the self-healing covers for smartphones, which were developed years ago by the South Korean company LG. However, smartphones are not load-bearing structures. For structural composites, self-healing functionality can be realized using microcapsules, vascular networks, or reversible polymers. Often, reversible polymers are softer and weaker than common epoxy. Vitrimers show high mechanical strength, and now there are many projects on development of vitrimer-based structural composites. This is an interesting option. Now, let us look at the wind turbine blade protection against the most common degradation mechanism, leading-edge erosion. In the project, Maintainer G, DTU Wind, and Indian National Institute of Wind Energy, carried out a survey of often observed damage mechanisms of wind turbine blades. This is the summary of results for Europe. What can we see here? Leading-edge erosion is the most common blade damage mechanism for recently installed wind turbines, and remains so, even for 5-year-old blades. But what about the cost contribution of minor damage on blades? In our earlier study, we evaluated the costs of minor damage versus the major failure costs. While major blade failure require much more repair time, more technicians, these events take place much more seldom. The estimation showed that the minor damage on blades, typically erosion, cost 12 times more than the major repairs. There exist a number of coatings and leading-edge protection solutions on the market. Many of them are very good. Excellent teams work on this problem. But the problem still exists. Here, you see, some newspaper reports. The repairs of wind turbine blades take millions of euros, and cost a lot of downtimes for wind park owners. How the leading-edge erosion of wind turbine blades takes place. Blades are rotating with high velocity under rain, hail, sun. Droplets hit the leading edge with velocity from 50 meters per second and higher. Day after day, year after year. Stress waves from these small impacts, propagating through the blade materials, are reflected on interfaces. The waves interact with inclusions and other materials. Polymer chains in the blade material are compressed and deformed. After several millions of such hits, a first microscopic crack is formed. The microcracks starts to grow, also due to moisture and further rain droplet impacts. The microcracks develop, interact, and small parts of materials are chipped off. The surface of blade becomes rough, and aerodynamic properties of blades are changed. The energy generation is reduced. We carried out literature study and identified main mechanisms controlling the coating damage resistance. Among them, one should mention viscoelastic damping, wave reflection on interfaces, wave scattering on inclusions, surface structures. One important factor is the thickness of coatings. The thicker is the coating, the more is the wave decay. The amplitude of impact stress waves, caused by rain droplet impact, is reduced when the wave travels through the thick coating. Mechanical loss coefficient of viscoelastic materials determines to which degree the energy is dissipated in the material. Raindrop impact causes the stress wave propagation in the coating. Elastic stress wave reaching interface between two layers can be partially reflected. The part of energy reflected depends on the acoustic impedance mismatch of the layers. Inclusions or particles, distributed in the coating layer, can also dissipate the impact wave energy. In our current project DuralEdge, micromechanisms of leading-edge erosion have been studied. Wind turbine blades, from old wind turbines, from Vindview Wind Farm, were cut and investigated, using X-ray tomography. The Vindview Farm was established in 1991, and decommissioned in 2015. The interesting observation was that the erosion damage starts, not from contact surface, where a rain droplet hits the blade, and highest stresses are expected, but rather from voids, and debonded particles, inside the coating. Here, you can see, the voids in the leading edge coatings, and start of damage from the voids. Further, computational model of leading-edge erosion has been developed. A computational model of wind turbine blade erosion includes typically several steps. Rain scenario, droplet size distribution, single drop impact model, wave propagation and damage initiation analysis. Fatigue model. At DTU Wind, a computational model of rain droplet hitting the blade surface was developed, based on the smooth particle hydrodynamics method. The effect of the droplet impact speed was investigated. It was observed that peak stress in the coating increases with increasing the impact speed. An increase in the droplet velocity from 50 to 100 meter per second leads to the 3 times higher peak stress. Next, we carried out parameter studies. The effects of droplet shape and impact direction on the stress field were investigated. It was observed that normal droplet impact creates highest local stresses as compared to oblique impact. Droplet's shape has a strong influence on the stress field, and, therefore, on the lifetime of coating. Ellipsoidal, compressed droplets lead to 15% higher peak stresses. Practically, it means that the common models underestimate the stresses in coatings. Further, void effect was studied. Even small voids in a coating drastically reduce its erosion resistance. Further, surface effects on the erosion were studied. In particular, surface roughness, and the availability of liquid film. It was observed that the rough surface increases the stress localization, leading to higher surface stresses close to the impact point. The wet surface reduces the stresses in the coating by 40–50%. The water film acts as additional protective layer. In order to estimate the erosion quantitatively, fatigue model of material degradation under random multiple rain droplet impacts was developed. For damage modeling, multi-axial damage model was used. The model, together with the rain drop impact simulations, allowed to predict the local erosion damage distribution. Here, you can see the damage distribution on the blade surface observed in the simulations. On the basis of our investigations, one can formulate some directions of improvement of polymer leading-edge protection coatings. First, one should enhance the manufacturing quality of coatings, prevent void formation, and ensure good attachment of particles to the matrix. Enhance the damping properties of the coatings, use multi-layer coatings with upper soft layer, prevent surface roughness. Here is an example of development of new advanced coatings for the blade protection. A team from Kingston University, in United Kingdom, University of Barcelona, Spain, and DTU Wind, developed polyurethane coating with graphene nanoparticles and hybrid nanoparticles reinforcements. Polyurethane, graphene composites, were prepared via in situ polymerization methods. Coatings with graphene and hybrid nano-reinforcements were tested for their anti-erosion performance, using the single-point impact fatigue testing methodology. It was observed that the nano-engineered coatings ensure up to 13 times higher lifetime than pure polyurethane coatings. We just discussed computational modeling of leading-edge erosion of wind turbine blades. But what is the general approach of using computational modeling for the development of wind turbine materials? The idea is to use the approach of computational micromechanics of materials. Computational model of materials is developed as representative volume element, including typical structural elements, fibers, sizing, matrix, voids. The representative element model is then subject to loading, reflecting the real service conditions. Then, the various material structures can be tested, compared, and optimal structure can be identified. An example of this simulation is the simulation of damage mechanisms in fiber-reinforced composites under tensile loading. We simulated the fiber debonding, fiber damage, and matrix cracking. In the computational simulations, an interesting observation was made, namely, that weaker and softer fiber matrix interfaces can prevent the matrix cracking in composites. In our project, we studied the strength and fatigue behavior of hybrid carbon glass composites. The different fibers fail by different mechanisms. While carbon fibers can fail by buckling and kinking, glass fibers fail typically by cracking. An interesting conclusion from our studies was that the strength of hybrid composites is a nonlinear function of carbon content. Another important factor is that the strength of the composites is strongly influenced by fiber sizing. Another application of the computational mechanics, in development of wind turbine materials and technologies, is the modeling of blade repair. This figure shows a computational model of scarf repair of blades. The model includes the composite scarf, adhesive layer, blade laminate, and coating. Using the submodeling techniques, we introduced voids and defects in adhesives and other elements. In the computational studies, the effect of manufacturing defects and voids on the repair quality was investigated. While the life extension efforts can delay the end of life of blades, at some stage, the old blade have to be incinerated or recycled. Both wind energy industry, regulators, and governments seek to find a quick solution to this problem. The European Union issued a number of directives concerning composite waste control, including Waste Framework Directive, Hazardous Waste Directive, EC Incineration Directive, EC Landfill Directive, and European Waste Framework Directive. These directives defined requirements toward waste management. Thus, the problem of recyclability of wind turbine blades is of especial importance now. Let us look at some numbers. 2.5 million tons of composites are in use in wind energy sector. A single wind turbine blade of 5 megawatts wind turbine contains 50 tons of plastic. 43 million tons of blade waste will be accumulated worldwide by 2050. 25% of them in Europe. Each megawatt of installed capacity corresponds to 9 tons of composite waste. Thus, it is a problem many companies work to solve better today than tomorrow. There exist several options for reuse or recycling of wind turbine blades. Here you see the reuse of large blades as bus station. The recycling methods are classified into following groups. Primary recycling or reuse is recycling products for the same use. Secondary recycling involves mechanical modification of the materials without the use of chemical processes like breaking the composite by shredding, crushing, milling. Tertiary recycling of composites is carried out by thermal decomposition, pyrolysis, or chemical decomposition, solvolysis. The surface properties of recycled fibers can be enhanced by obtaining cleaner or active surfaces. This can be achieved by changing thermal regimes, modified pyrolysis methods using lower temperatures for carbon fibers, or higher temperature for thermolysis, to achieve low char residue on recovered fibers. One option to make composites recyclable is to replace common epoxies by recyclable polymers. Thermoplastic composites have some disadvantages as compared to epoxy. For instance, higher processing temperatures, higher costs, different cooling rates. On the other side, several groups work on recyclable thermosets. Recyclable thermosets have the potential of combining the best of two worlds, recyclability and high performance, of cross-linked thermosets. Thermoset recyclability can be ensured by introducing degradable, or dynamic covalent bonds in the polymers. The dynamic response of these bonds should be triggered by an external stimuli. The external triggers can be, for instance, thermal or acidic loading, catalysts, or ultraviolet light. The triggered degradation of thermosets can be realized by cleavable linkages in the polymer network. There are a number of requirements to the degradation stimuli. They should not trigger degradation during service time or reduce performance. Now, we are DTU Wind, start a new project, which should provide computational model, and technical decision, and optimization basis, for recycling of wind turbine blades. Here, you can see the schema of computational modeling of separation of composite components under physical loading. We consider here microwave pyrolysis as example, but the model is easily expandable to other technologies. Let us make some conclusions. Critical material science problems of wind energy development include ensuring durability and extending lifetime of wind turbine blades. Sustainability and recyclability. Easy maintainability of wind turbines. Most often observed failure mechanisms of wind turbine blades include leading edge erosion, adhesive joint degradation, trailing edge failure, buckling, delamination, and blade collapse. Directions of development of composites include using lightweight carbon fibers, but also high-strength glasses, recycled and bio-based fibers. Bio-based resins, natural fibers, self-sensing, and self-healing composites are promising developments, and are under development now. Coatings can be modified and optimized to mitigate the erosion of blades. Computational modeling, including the material structures, allows optimization of blade materials, and better understanding of blade degradation mechanisms. Here, you can see some references related to this area. Feel free to drop me a line if you need these publications. Now, a little bit about our activity and projects. We have now several running projects, in close collaboration with industry, Danish, and foreign universities. The project DuralEdge, Durable Leading Edges, for high-tip speed wind turbines blades, is carried out, in collaboration with leading wind turbine manufacturers, Vestas, Siemens Gamesa, LM Wind Power. The project seeks to develop understanding of leading-edge erosion mechanisms. The project, Maintainergy, Maintenance and Repair Strategy, for Wind Energy Development, is carried out, in collaboration with Indian Consortium, and seeks to optimize the blade maintenance technologies. The networking project, Structural Health Monitoring, and Maintenance of Wind Turbines, is carried out, in collaboration with New York University, and Tufts University, in the United States. A few words about myself. I was born in Ukraine, made my postdoc in Technical University Vienna, was working 10 years at the University of Stuttgart, and moved to Riso in 2005. Thank you for your attention.